Hello, we are the Michigan Mars Rover team, and we are proud to introduce to you our 2024 Rover. We have learned a lot from last year's competition and done a thorough re-evaluation of all our designs. With new training modules and increased emphasis on recruiting and outreach, we have a team of over 100 members who are working hard to design and build our new Rover.
This year, we opted to redesign our Rover for increased performance and strength. We've adapted our aluminum welded torsion box chassis for high loads and redesigned our differential bar for superior kinematics. The 3D printed tires and rocker boogie suspension allow the Rover to maneuver through a rock garden and climb slopes up to 30 degrees. We also completely redesigned our drive system to utilize brushless, frameless motors and custom planetary gearboxes to optimize for torque transfer, control, and mass. Our 5-degree of freedom robotic arm has also seen significant upgrades. The base joint translates linearly across our torsion box for repeatable tasks. We have kept cycloidal transmissions with brushless motors for our high-load case joint. In addition, we combined our 2 wrist joints into a single compact differential drive. The lead screw-driven end effector is capable of performing precise servicing tasks and can grasp objects up to 5 inches and 10 kilograms. Inverse kinematic control of the arm allows the operator to precisely move the end effector to a specified position.
Our rover utilizes a 3-axis Cartesian system with a coring mechanism to acquire soil samples from 10 centimeters below the surface. Additionally, the end effector has a sensor for recording the soil moisture and temperature at this level. All of our samples are analyzed in our instrument sampling and handling box. This year, we have 3 life detection tests. Our Benedict's test tests for reducing sugars and can detect simple carbohydrates. Our next test is our ethanol autofluorescence test, which can identify chlorophyll. My final life detection test is the ninhydrin test, which can detect amino acids. This year, we have also been working on troubleshooting our in-house Raman spectrometer, which has the capability to recognize biosignatures such as keratin and carotenoids. Furthermore, our multiple cameras will assist us in choosing test sites as well as taking a stratigraphic profile for analysis. A panorama is taken with a stereo camera so we know the depth of every pixel.
The Rover's electrical design has broadly switched to a more distributed system for better wire management and increased reliability. Our multiple custom boards each have their own power converter and microcontroller circuits. Wiring is made simpler through a daisy-chained CAN bus, which streamlines communication between devices. Several new PCBs have been designed this year. This includes a 12-volt brushed DC motor controller with encoder and limit switch functionality. Next, our science board provides power and controls life detection test electronics. Finally, the power distribution board drops down the battery voltage for essential devices. For powering the Rover, our 36-volt battery gives us more than 1 hour of continuous operation with an accessible e-stop for quickly turning off the Rover. The Rover uses 2.4 GHz radios that allows for up to 1 kilometer line-of-sight communication.
Last year, our software team overhauled our entire codebase to use ROS. Now we are focused on building atop this robust framework for the new challenges faced. To autonomously detect the orange melon in water bottle, we fine-tuned a neural network model based on YOLO V8 with 100 diverse images. The resulting model is optimized for a Jetson via NVIDIA TensorRT to achieve real-time object detection. Stereo vision is then used to locate objects in 3D space relative to the room. We can propagate their locations to global space thanks to our new dual GPS system. Both receivers use RTK to acquire centimeter-level accuracy. An invariant extended Kalman filter is used to optimally fuse the kinematic model of our Rover with sensor measurements. A camera with a zoom lens has been added to detect Bruco markers from long distances. The trajectory following algorithm has been updated to use cost mapping and train with untraversable spots. These new features are battle tested in our in-house simulator before being deployed to the physical Rover. Automated regression tests using the simulator engine protect the integrity of our main code branch.
We have prioritized early integration and testing to verify Rover designs. We continue to use development boards to integrate software and hardware for Rover systems in parallel. Operator practice and mock missions are our top priority to develop mission strategy. A drone for the delivery mission will help Rover operators identify points of interest. We use our mock lander as well as our university's robot playground and Mars yard to simulate URC conditions. We are excited to showcase our new Rover and confident in our ability to succeed at the 2024 University Rover Challenge. Thank you for your consideration.
Go Blue!